All right, so now we're going to go over some common 2D transformations. And here's a few of them. So these are transformations from R2 to R2. This is a reflection, an expansion, a shear, a projection, and a rotation. And here are the standard matrices for each of these. So if you want to reflect a vector, any vector across the y-axis, you multiply by this matrix, etc., with each of these matrices. So I'm going to show you how to find a matrix that does transformation in R2. So let's find the standard matrix that does the following transformation. All right, so we have our x, y coordinates. Draw this little box here. I'll explain what this box means in a second. And the resultant box, it's a rectangle, is this one. This dimension is twice, and this dimension is 3 times. Okay, so we start with that little box, and then we expand both in the y direction and the x direction by a factor of 2 and 3 respectively. Okay, so what we want to think about with this transformation is what it does to the coordinate vectors. And that's what this little box is telling us. The sides of this box are the coordinate vectors. So what this picture is telling us is that the x2 coordinate vector or y coordinate vector doubled, and the x1 coordinate vector or x vector tripled. Okay, so it's telling us that the transformation took E1 to the vector 3, 0, and it took the vector E2, that's this y vector, 1, 0, or 0, 1, excuse me, to 0, 2. Okay, that's what the transformation did. And from this, we can figure out what the standard matrix is. Because remember, the standard matrix by that theorem from the last section is just TE1, TE2, which gives me 3, 0, 0, 2. And let's check this by looking at what happens to some other random vector. Let's consider what happens to the vector 1, 1, this diagonal here. And you can see that this diagonal is precisely the corner of the box, the original box. So we can guess that this diagonal is going to go to the corner of the rectangle that results when we transform this box. So it's probably going to go to this, and let's see that play out. So let's take the vector 1, 1 and multiply by this matrix. And you can see that these are the weights on those two columns. So we're going to get 3, 0 plus 0, 2, which is 3, 2. Exactly what we'd expect in this picture. So this is nice. Once we know what the transformation does to the coordinate vectors, we know what it does to any vector in this space. And really, this picture isn't capturing what happens to any vector in this whole space when we stretch it by 2 in the y direction and by 3 in the x direction. All right, let's do another example. And the next example is a generalization of the rotation transformation that I had up here. So this rotation here is through 45 degrees. And now I'm going to generalize this to any angle. So find the standard matrix A for rotation counterclockwise theta degrees. All right, so we'll draw our starting matrix, which is this little rectangle, this little box, and then we'll draw a rotating theta degrees. I'm going to draw it on a separate graph here so I can see it easily and label things a little more easily. And this angle is theta. Okay, so the key is to figure out what happens to the coordinate vectors. So here's our E1, and here's our E2. So those two vectors go to this vector and this vector. And we got to figure out what the coordinates of these new vectors. This is TE1 and TE2. And to do this, I need to use trigonometry. So I'm going to take this and draw it big so I can see the angle a little more easily. So we're zooming in on this section of the graph. And we'll put our angle here. And so the new coordinates of this vector, well, they're going to be in terms of theta. So this is going to be the sine of theta, this side. And this is going to be the cosine of theta. And the hypotenuse is 1 because the original vector had length 1. So this new vector, TE1, is going to be cosine theta, that's its x coordinate, sine theta, that's its y coordinate, or x2 coordinate. And now we got to figure out what's going to happen to TE2, that's this vector. So let's zoom in on this one. Let's like here. And theta is not this angle anymore. It's the angle here, because if this rotates theta, then this E2 is going to rotate off the y-axis theta. So this is theta. And that's going to help us write that angle. That angle's theta. That's just a fact of geometry. And so this side is going to be the cosine of theta. The vertical side is going to be the cosine of theta. And the horizontal side is going to be negative sine theta because it's going to be going backwards in the x direction. So TE2 is going to be negative sine theta cosine theta. And we combine those two facts to find our A. So our A is going to be cosine theta, sine theta, negative sine theta, cosine theta. And that is our standard matrix for rotating theta degrees. And this matrix comes in quite often in computer graphics, stuff like that, where we're rotating a bunch of things and seeing what happens. Okay, so let's continue on with another example. I want to find a standard matrix that rotates 90 degrees, and this is going to be counterclockwise. If it's not mentioned, assume it's counterclockwise. And then we're going to reflect across the line y equals x. So let's track what happens when we do these two operations. So we have this, our starting box, a little square here. We're going to rotate 90 degrees. We'll get a square that's over here. And my new E1 and E2, well, this will be my new E1. And this will be my new E2. But this is my old E1 and E2 here. So that's the first, that's the rotate 90 degrees. And then if we reflect across the line y equals x, use purple for this, then the E1 goes, mirrors across this, goes over to here, and my E2, erase this here, make this blue here. So that's my old one, and then my old E2 goes down here. So this is my resulting box here. Okay, so that's the path of E1 and E2. We charted what happens to E1 and E2. So TE1, its final location is 1, 0. And TE2, the final location of E2 is 0, negative 1. And so my standard matrix, which we call A, is going to be 1, 0, 0, negative 1. And if I take any vector and multiply by this matrix, it'll do these two operations. Rotation and then reflection in this order.